Okay, let us set aside predicate calculus and return back to propositional logic. Recall that we had found ways of writing sentences in propositional logic. We had found rules of inferences. We could prove theorems. We could find the truth value of new sentences. However, we found that those methods were computationally not very efficient. So AI has developed more efficient methods. One of those methods is called resolution theorem proving. Let us take an example to illustrate how resolution theorem proving works. So imagine there is a robot, and this robot is working on an assembly line. It's a factory robot. And on the assembly line are coming various kind of widgets. The robot's task is to pick up each widget as it comes on the assembly line and put it in a truck. However, there are some humans in this factory who play a joke on the robot once in a while. They glue the widget to the assembly line belt so that when the robot tries to move it, it cannot move it. But the robot is a smart robot. This is a logical agent. So when it cannot move it, it uses its logical reasoning to figure out that the box is not liftable. And the moment it knows that the box is not liftable, it lets go of the box. It moves on to the next one. Everyone got the story? All right. So let us suppose that the robot begins with some knowledge in its knowledge base. And this knowledge in its knowledge base that it begins with says that if cannot move, then it implies that not liftable. Now it tries to move the box, the next box on the widget. Its percepts tell it it cannot move. It needs to prove that it's not liftable. Now, of course, this is a trivial example. I'm sure you all understand it. You could potentially apply simply modus ponens to prove that it's not liftable. If P, then Q, P, therefore you can infer Q. But we'll use this example to show how resolution theorem proving works. So the first step in resolution theorem proving is to convert every sentence into a conjunctive normal form. A conjunctive normal form of a sentence can have one of three conditions. It can have a literal, that can be either a positive atom or a negative atom. It can have disjunctional literals, like here, can move or not liftable. Or it can have a conjunction of disjunctional literals. In this example, the third condition doesn't occur. So the first thing we must do is to take the first sentence. The negation of not move implies not liftable, and remove the implication because an implication cannot occur in conjunctive normal form. So the first thing we need to do is to rewrite this sentence, the first sentence, to remove the implication, because implication cannot occur in a conjunctive normal form. So now we use the implication elimination rewrite rule to rewrite this in the form of can move or not liftable. Remember, that was alpha implies beta becomes not alpha or beta. So the not of negation of can move becomes can move or not liftable. So we have done it for the first sentence. This is now in a conjunctive normal form. We can do the same thing for the second sentence, but wait, the second sentence already is in a conjunctive normal form. We don't have to do anything. Now the robot wants to prove that that box is not liftable. Resolution theorem proving is like proof by refutation. To do proof by refutation, we'll take the negation of what we want to prove. We wanted to prove not liftable. We'll take its negation, which makes it liftable. Okay, so now we got three sentences. This was the first sentence that the robot was bootstrapped with. We have just converted into a conjunctive normal form. This was the sentence that came from its percepts. It saw that the box cannot move. And this is the sentence, rather than negation of the sentence, the refutation of the sentence that it wants to prove. So we have three sentences now. The first sentence came from the bootstrapping of the robot's knowledge base. This is the axiom that the robot assumes to be true. The second sentence came from its percepts. The robot tried to move the box. It could not move it. The third sentence is coming from taking the negation of what the robot wants to prove. It wants to prove it's not liftable. So it's going to take the negation of it and then show that it's going to lead to a null condition that we'll view as a contradiction. In resolution theorem proving, we always begin with a literal in the sentence that we want to prove. So here that sentence is liftable. And we look for a sentence that contains the negation of a literal in this sentence that we want to prove. So the sentence here was liftable. Sentence S1 contains a literal, which is a negation of that. So we pick S1 and not S2. Note how efficient it was to decide which sentence in the knowledge base to go to. The sentence contained a negation of the literal. So liftable and not liftable cannot both be true. We know that. And therefore, we can eliminate them. This is called resolution. We resolve on liftable and we remove them from the sentences. Now, we were at sentence S1. That leaves us with can move. So now we pick a sentence that has the negation of the literal can move. Sentence S2 has a negation of that, and we can resolve on can move. They cannot both be true. When we resolve on both of them, those get eliminated as well. And now we see we've reached a null condition. This null condition represents a contradiction, and now we can infer that liftable cannot be true. Therefore, not liftable is true. The robot has proved not liftable. In this case, it appears as the resolution theorem proving is more complex than modus ponens. In general, it is not. It just appears here because this condition happened to fulfill the form of modus ponens directly. In general, deciding on which sentence to apply the modus ponens on and how to combine those rules of inferences turns out to be computationally harder than deciding how to apply resolution theorem proving.